Welcome to our invited Spotlight Talks, Trends in Safe Learning for Robotics. This is for the IROS 2021 workshop on real-world robot autonomy. We are happy to share 8 invited Spotlight Talks with you today. We have contributions to the part 1, which is on safe learning-based control, part 2, which is on safe reinforcement learning, and part 3 on certifying learning-based control.
We will start with 2 safe learning-based control contributions by Aditya and Hugo.
We present our work on safe learning-based control undertaken at the Advanced Controls Research Laboratory at UIUC under Dr. Homanga. My name is Aditya. Standard learning-based control uses learned models with an optimal control. These include reinforcement learning and model-predictive control. However, modeling errors, disturbances, and learning transients can lead to unpredictable performance and even loss of stability. Therefore, one attempts feedback motion planning with a safety controller tasked to handle the uncertainties. In our work, we use the L1 adaptive control for safety augmentation because of its features of quantifiable transient bounds, robustness margins, and the ability to absorb nonlinear learned models. The design principles for the safety controller are the ability to incorporate learned models, ability to publish certificates of guaranteed performance, which can be easily incorporated into high-level reinforcement learning or MPC algorithms, and the fact that safety remains decoupled from learning. Only performance depends on learning. Safe operation should always be guaranteed. Motivated by the challenges, we propose the learning-based control pipeline where the foundation is control theoretic in the form of contraction L1 control. The performance is brought in using machine learning. And once again, under the principle that safety remains decoupled from learning. We now discuss our work on the foundation, which is the contraction L1 control for safety. We use contraction-based control to ensure trajectory tracking for the nominal known system, and the L1 augmentation compensates for the uncertainties while using the Riemannian energy as a Lyapunov functional. The guarantees provided by the contraction L1 control are in the form of invariant tubes around any feasible trajectory. The tube width, which can be considered as a proxy for performance, can be varied by tuning the control parameters, albeit as a trade-off with robustness. We now bring in model learning in the form of Gaussian process regression to provide more performance. As mentioned, contraction L1 provides safety in the form of invariant tubes, the width of which corresponds to the amount of uncertainty. With better model knowledge, however, the tube width decreases and one moves towards more optimal control. For example, we would like to move from slow to aggressive performance as a function of learning while maintaining persistent safety throughout the transition. We now bring all the components together in a unified architecture where the contraction L1 ensures the existence of safety tubes. The Gaussian process mean of the estimates are propagated to the planner and the contraction control, whereas the L1 control compensates for the variance producing high probability tubes. Unlike contraction L1 control previously, the use of learning leads to better performance, that is smaller area tubes, without requiring the trade-off with robustness, although the option is still present if one would like to use it during the initial phases of poor model knowledge. If we consider a Dubin's car model simulation, and the vehicle is tasked to travel from left to right while traversing some obstacles. In the first case, using only the contraction-based control, a few of the system trajectories collide due to the uncertainties. However, with the contraction L1 control, the high-level planner incorporates the tubes to produce safe, albeit poor optimality trajectories. By bringing in learning, the tubes shrink and the planner can produce much better trajectories while the safety of the system is always guaranteed. And our approach is model planner agnostic. We use both NPPI and BitStar in our simulations. We now discuss our work on learning certified control policies. As previously mentioned, we augment baseline contraction control in our case with L1 adaptive control. As the models are updated, we need to learn updated baseline controllers as well as with certified performance. Consider the torque limited pendulum. Due to the torque limitation, finding a certified controller for the swing up is infeasible. That is, finding a contraction metric valid over a connected region containing both the stable and unstable equilibrium. The same problem persists in finding a Lyapunov function-induced region of attraction to construct feedback policies. However, trajectory optimization-based methods like RL and MPC can produce a trajectory to reach the unstable equilibrium. So how to generate feedback policies for tracking such trajectories? We propose a method of jointly learning feedback policies and the associated regions of attraction. We call such sets as incremental regions of attraction, as they combine the ROA properties for tracking trajectories instead of stabilizing just equilibria. Hence, we use the qualifier incremental. Incremental ROAs are computed offline and can be snapped onto any feasible trajectory. We use neural network optimization and verification for this purpose. Coming back to the task of stabilizing the swing-up trajectory for the torque-limited pendulum, using our method, we can snap on an incremental region of attraction for the trajectory. The synthesized feedback law ensures that all trajectories initialized within the incremental ROA converges to the desired trajectory. On the right, you can see the swing-up from 9 different random initializations of the torque-limited pendulum. Here are the references for the presented work. Please pause the video to take a look. I would like to mention our collaborators at both UIUC and Georgia Tech. Thank you.
Good morning and welcome. I'm Rosolia and I'm a postdoctoral scholar at Caltech. And in today's Spotlight talk, we are going to see how we can leverage lessons from the model predictive control community to design safe and efficient model-based reinforcement learning algorithms. So let's start by summarizing which are the key components that we need to compute in order to synthesize a model predictive controller. Let's say that our goal is to compute steering and acceleration commands for an autonomous vehicle driving over a racetrack. Using a model predictive control methodology, we would first forecast the trajectory of our vehicle over a short time horizon, and afterward, we would apply to the system the first control actions associated with our predicted trajectory. And as we can see in this example, a model predictive controller plans the trajectory of the system over a very short horizon. And for this reason, the controller might take short-sighted control action that would compromise the safety of the closed-loop system. And for this reason, we usually want to constrain the predicted trajectory to land in a safe region of the state space from which we know that the control task can be successfully completed. For instance, in this autonomous racing example, we want to constrain our controller to predict a trajectory that slows down right before entering the curve. And furthermore, in autonomous racing, we really care about performance over the entire racetrack and not only over a short prediction horizon. And for this reason, we want to have a terminal predicted cost which approximates the tail of the cost beyond our prediction horizon. For instance, in this example, our predicted cost will encourage our vehicle to take a very sharp turn. And in standard model predictive control strategies, we usually leverage our knowledge of physics to compute a prediction model, and the safe set and the value function are constructed using the prediction model and optimal control theory. In the prediction model, the safe set and the value function are the 3 key components that are needed to synthesize safe model predictive control strategies. And these 3 key components are used in several methodologies from the control community and the reinforcement learning community. For instance, in model-based RL, we usually use historical data to estimate a prediction model. On the other end, in some model-free reinforcement learning strategies, our goal is to construct value functions. And finally, the safety critical control community, we would like to estimate the safe region of the state space from which our task can be successfully completed. And in today's Spotlight talk, I hopefully will convince you that in order to perform safe and efficient learning, we need to operate at the intersection of these 3 spheres. And we're going to see how a strategy that learns a value function, a prediction model, and a safe set works on an autonomous racing experiment, where our goal is to drive a vehicle over a racetrack as fast as possible. In order to design a learning controller for this task, we are going to use a standard model predictive control methodology, where we're going to leverage historical data to learn a prediction model, a safe set, and a value function. And we tested such strategy on our autonomous vehicle platform. Here at the first lap, we used a standard model predictive controller to drive the vehicle on the center line of the road at a low speed. And we use historical data to estimate these 3 components. And so here we see that after only 10 laps of learning, our controller is able to operate the vehicle at the very limit of its handling capability. Indeed, that you can hear that the tires are squealing. And here we are only using experimental data to update our controller. And we tested this strategy also on the California Proving Ground, which is a real test track in Southern California. And here, once again, at lap 1, we use a simple path following controller that tracks the center line of the road at a low speed. And we use this collected data to iteratively improve the performance of our controller. And what we saw is that only after 16 laps of learning, the controller realizes that in order to minimize the lap time, the vehicle has to cut inside the curves, and furthermore, you can hear that the tires are squealing at every curve, meaning that the controller is operating the vehicle at the limit of its handling capability. And so with this, I would like to thank you for your attention. I'll be happy to take any questions.
Now we have a contribution by Homanga on safe reinforcement learning.
Hi, in this video we'll talk about the paper Conservative Safety Critics for Exploration. This is joint work with Aviral Kumar, Nicholas Reinhardt, Sergey Levin, Florian Shkriti and Animesh Garg, published in ICLR 2021. The motivation for this paper is deploying robotic systems in real-world settings where safety is a very important concern. Examples of these sort of settings include robotic surgery, space exploration, legged locomotion, self-driving, and dexterous manipulation. In all these cases, we need to be able to evaluate safe behavior of the agent before deploying them in order to prevent catastrophic failures. The specific problem that we target in robotic safety is that of safe exploration. The formulation is that of reinforcement learning, where the agent interacts with the environment and gets a reward signal. The problem of safe exploration then is how does the agent explore the environment in order to get high rewards while at the same time ensuring that it doesn't incur failures. We don't want the agent to have any catastrophic failures during training because they are costly and they may damage the robot and also harm the people interacting with the robot. So how should an agent learn without having these catastrophic failures during training? One of the ways to do that is by enforcing and respecting constraints that bound the probability of failure during training. We can formalize this constraint by assuming a sort of binary signal from the environment that indicates whether a failure has occurred. This is the most general setting that we can assume because it doesn't take into consideration any shaped safety function from the environment. So given this general sparse binary signal from the environment, we can create constraints such that the constraint indicates the expected probability of failure. And then the objective for the agent is to perform well in the task, that is gain high cumulative rewards, but ensure that the value of the constraint is never greater than the threshold. To do this, we can formulate a constraint Markov decision process objective where we need to find the optimal policy pi star that maximizes the value with respect to the task reward r, while at the same time ensuring that the probability of failure is less than a certain threshold chi. We can see that the probability of failure actually can be translated to a value function based on the safety signal that the agent receives from the environment, which is a sparse signal in our case. So given this setting of finding the optimal policy pi star, we can cast it into an optimization objective where we consider the expectation with respect to a Q function and have a constraint on the safety Q function QC. We can solve this optimization through the method of Lagrange multipliers, where we introduce a dual variable lambda and perform minimax over this objective in an alternating fashion. This gives rise to the safety critic algorithm that we describe in the paper. One of the important things to note here is that there can be estimation error in the safety critic QC. Since we want the agent to respect the safety constraint at all costs, we can be conservative. By that, what we mean is we can explicitly train the safety critic such that its value is always an overestimate of the underlying critic's evaluation at a particular state in action. So if this is an overestimation, then although there might be some error, the agent always errs in the side of caution. To do this, we take inspiration from the conservative Q-learning paper that provides a theoretical framework for learning a Q function that is a provable underestimate of the underlying Q function. We take the CQL objective and flip its sign so that we get an overestimate instead of an underestimate. Based on this, we can go back to the safety critic algorithm and train the critic with Q-learning based on CQL. We show that this algorithm has some appealing theoretical properties. For example, we can always bound the expected probability of failures, which translates to a value function v sub c, by a number that is sufficiently small. We can also show that although the agent takes safety into account during training, its convergence to the optimal Q function of the task reward is not severely bottlenecked. We show experiments on a number of different environments. For example, in manipulation, the agent has to push the block without the block toppling, and we compare against state-of-the-art baselines that involve an ensemble of Q networks, constraint policy optimization, CPO, and the Bayes algorithm. It doesn't take safety into account. We see that our approach, CSC, performs much better in terms of average failures. It has very low failures while at the same time not compromising on task reward. Similarly, we evaluate on a locomotion task where the agent needs to run as fast as possible without. Even here we see that the cumulative failures are much lower compared to the baselines. In summary, we presented a framework for reinforcement learning with safety constraints. We proved theoretical bounds on the objective proposed in the paper, and we verified the approach empirically on a suite of manipulation and locomotion tasks. Thank you.
Next, we'll hear from Guanya, Michael, and Sydney on certified neural learning control approaches.
Hi everyone, welcome to the IROS workshop. My name is Guanya Xu, a PhD student from Caltech. My research is on the intersection of machine learning and control theory with applications in robotics. I'm very excited today to share our recent work on neural net family, a line of work for learning-based nonlinear control in dynamic environment. As you can see here, neural net family demonstrates new capabilities in very dynamic environment. In neural lander, we achieved agile landing with complex ground effect. In neural swarm, we achieved close proximity flight for dense swarm. And in neural fly, we achieved agile flight in dynamic wind conditions. The motivation behind this work is real-world decision-making is very hard. So here comes the question, can we broaden the successful horizon of deep learning? Deep learning already solved a lot of challenging decision-making problems in this box. For example, it can play Atari game, it can defeat human in a game of Go, and it can play a Rubik's Cube using manipulator. However, it is unclear, at least to me, whether we can extend these successes to safety critical system. For example, aerospace. I want to use deep learning to optimize design, manufacturing, and operation of our aircraft, but I need some guarantees. It is from some aerospace director when I visited Caltech. Apparently, we need to think much more carefully when we apply deep learning in these safety critical systems. The idea of this work is combining control theory and machine learning. Instead of end-to-end learning, we have some prior knowledge from physics, and we combine this prior knowledge with data and learning, and we get a mixed and a modular system for control synthesis. And we apply this mixed policy to hardware. And I want to emphasize that because this system is modularized, and we can integrate learning and control theoretical result nicely here. By the way, many other people also work on this topic. For example, we have a control-based learning seminar series, which is organized by me and colleagues. We also have our own conference, L4DC. More specifically, the idea of neural network family is to learn the residual dynamics. In this dynamical system, F is the nominal dynamics from physics, and G is the unknown residual dynamics. For example, let's consider the John Lanning case. F is just the rigid body dynamics in the free space, which is very easy to model. And G is the complex aerodynamic interaction between the John and the ground, which is much harder to model. So the goal is to use deep learning to learn the hard to model part G directly from data and combine this with the nominal dynamics to design controller. I would like to highlight that the learning process on G is not arbitrary. We need some control semantic constraints to constrain the learning process and the behavior of deep neural network. And here are two examples from this methodology. The first one, as you can see in this video, is neural lander. We can land the drone very smoothly, and the drone can track a circle trajectory very close to the ground. Actually, it is only a few millimeters to the ground, but it didn't touch the ground. And the second example is neural swarm. As you can see in this video, we can achieve very agile close proximity flight in a 16 robot team. More specifically, the controller design we used in neural swarm and neural lander is feedback linearization. And to constrain the Lipschitz property of deep neural network, we use spectral normalization. And with this constraint on the Lipschitz property, we can guarantee stability. And also in neural swarm, which is a little different from a neural lander, the unknown dynamics also depends on neighbors. So we use DeepSet to encode it. For more details, feel free to check out these two papers. And this idea also generalized to neural swarm in a multi-environment setting. In NeuroFly, the residual dynamics G is also a function of the environment C. For example, C could be the wind condition for flying drone. And the key idea of NeuroFly is to decompose this G into two parts. The phi part is the representation shared by all environments. And the A part is a linear weight, which is environment specific. And the idea is we use meta learning to train a representation phi, and we use adaptive control to update the linear weight A. And here is some result, as you can see in this video. The baseline method, if we increase the wind suddenly, it's very hard for the baseline method to go back to the original point. However, for our method, as you can see, even if we suddenly increase the wind, the drone can very quickly and very smoothly go back to the original point using adaptive control. Okay, thanks for the listening, and here are the references.
Hi, my name is Michael Everett, and today's talk is going to be a quick summary of some of our recent work on developing certifiable learning machines. So what do I mean by these certifiable learning machines? There's a whole bunch of different sources of uncertainty that can come into these control systems that use neural networks. And so in robotics, we see these neural networks applied in perception, planning, and control tasks all over the place. So this uncertainty shows up at the input of neural networks because you have incomplete training data, you could have imperfect sensors, and that uncertainty at the inputs makes its way all the way to your neural network's outputs, which end up ultimately being decisions that your system makes. So what we need to do is develop tools that can allow us to quantify the set of possible outputs that your neural network is going to produce, given that you may know something about the input set that could be coming in. And so I show here down on the bottom a couple of different instances that I'll go through really quick, where we've been looking at doing this type of analysis for neural networks in isolation for things like classification, in feedback loops, so you have a learned policy, which is a neural network, as well as in the model-free reinforcement learning case, we can add some robustness using these tools. So one of the first things I want to talk about really quickly is thinking about how do you just map a set through a neural network, which the neural network is very high dimensional, very nonlinear. So there's going to need to be some amount of approximation to be able to do this in a reasonable amount of time. So some of our work, just to give an illustration of it, takes a set coming into the neural network. So this could be, bounds on different elements of your state vector or your image. And we pass those through where we're showing here in this animation, rather than exhaustively sampling all the different points in this set, which you're never going to be able to do completely, we instead are partitioning the set and looking at different cells in that partition, propagating those through, and then like refining these bounds over time to try and approximate the true shape of the output set. So once you have that output set, it's useful for all sorts of things and doing analysis of systems, which I'll talk about in the next couple of slides. One of the things you can do is improve the robustness of deep reinforcement learning. So rather than having a policy that ends up being something like you'd see in deep Q networks or deep Q learning, where you have just taking the action that maximizes your Q value function that's been learned. Instead, what we can do is a robust implementation of this policy where we think about what's the best action given that we don't have exact knowledge of the current state of the system. So we can do this sort of mini-max optimization and run it really efficiently using the tools I described on the previous slide. Down in the bottom right, you kind of see an instantiation of this where if you do this robust deep reinforcement learning without thinking about partitioning, you end up with a little bit of a conservative policy. It will still be safe, even though there's some uncertainty in where the blue agent's position is. And then when we add our partitioning ideas in, we end up getting a much more fast solution where the orange agent gets to its goal much quicker. And we showed this idea extends to image space as well, where we have a Atari game where the attack is being done in the pixel space, where the position of the ball on the screen is being spoofed. And that's just a few pixel changes enough to confuse and attack a deep Q network policy that isn't thinking about it. And we could bring the robustness back in by adding in this idea. So the last thing I want to talk about is just bringing this analysis into a closed loop system. So what we've been doing recently is thinking about reachability analysis, where you have, say, a UAV pictured over here on the right that has some control policy. And you want to understand all these different sets in the future, which are the set of all states that the system could occupy in time. So if we assume we know something about the system's dynamics and we have a pre-trained policy, we can end up bringing some of these tools into the closed loop analysis and compute these reachable sets. And that's shown down here in this animation, where we're also bringing in the partitioning ideas to refine those estimates of all the different states that the system could be in the future. And so this allows us to basically provide that stamp of approval before you turn your robot on. And it says, even though you have a neural network that's going to be making decisions, we can still guarantee that your system isn't going to enter the avoid sets, pictured here as these red regions, and that your system is going to end up in the goal region where you'd like it to. So I'll point everybody to the code for a couple of these papers that I described, which is down here in this GitHub link. I'd be really excited if you try it out and let us know how it works. And here's some references. You can find out more about the papers, or feel free to reach out anytime. Thanks.
Hi everyone, my name is Sydney Katz, and I will be talking about some joint work with Anthony Corso and Chris Strong under the direction of our advisor, Professor Michael Kokendorfer, on verifying image-based neural network controllers using generative models.
An example of an image-based verification problem is the autonomous taxi problem. In this problem, we assume we have an aircraft situated somewhere on the runway, and that we've been given a neural network that was pre-trained to guide the aircraft along the center of the runway using downsampled images taken from a camera on the wing of the aircraft as shown on the left. One safety question we could ask is, will the neural network controller ever guide the aircraft to leave the runway, which could be dangerous? Another question we could ask is, not only will the aircraft stay on the runway, but will it also be guided towards the center of the runway? Our goal in this work is to produce formal guarantees that these properties will be satisfied for all possible trajectories down the runway. While generating these formal guarantees for controllers that take the true state as input rather than image observations is possible with current state-of-the-art techniques in closed-loop neural network verification, image inputs add extra complexity. In particular, we identified two key challenges. First, the inputs are high-dimensional. Even the downsampled images we use in this work still have 128 pixels and therefore a 128-dimensional input to the neural network. Second, and possibly even more critically, the set of plausible inputs is not well defined. While we know for a grayscale image all pixels can take on values between 0 and 1, this represents the space of all possible grayscale images. What we actually care about is a subset of the images in this space that look like a runway. With these two challenges with image inputs, we cannot directly apply the state-of-the-art tools developed for state-based controllers with image-based controllers. We propose to overcome these challenges by training a generative model to approximate the set of plausible input images. The technique works as follows. We assume we have a control network that takes in an image and outputs a steering angle, providing us with a mapping from images to actions. We now also have a generator network from our generative model that takes in a state and some randomly distributed latent variables and outputs an image, providing us with a mapping from states and latent variables to images. Noting that the output of the generator is the same as the input to the control network, we can concatenate these networks to obtain a network that maps from a well-defined set of state and latent variables to actions. With this new mapping, we can now answer the questions we posed at the beginning of the presentation using state-based verification techniques by verifying over all states and latent variables. Here's a preview of some of the results. The video on the left shows the images produced by the generative model we trained using a generative adversarial network architecture compared to the true images. We can see that visually they match pretty closely. In the paper, we also provide an evaluation metric to quantify the ability of the generative model to adequately capture the set of plausible input images. The figures on the right show the guarantees we obtained with respect to the set of images generated by the generative model. We use forward reachability techniques to test whether the aircraft will be guided to the center of the runway and obtain an over-approximated reachable set as shown in the top left and bottom figures. The rightmost figure shows the result of using backwards reachability to determine if the aircraft will ever leave the runway. The gray cells represent a safe set in which to operate. This wraps up our short introduction to this work. If this presentation piqued your interest, check out the full paper for more details. And of course, don't hesitate to reach out with questions.
The last two contributions are on safe set certification for learning-based control by Jason and Kim.
Hi, I'm Jason. I'll be presenting about my research on using data-driven methods for safety control under model uncertainty. This is a joint work with Fernando Castaneda, Pique Zhang, Wonseok Zhang, Claire Tomlin, and Kaushal Srinas. The main motivation of our project is that model-based controllers have a problem inherent to their nature, model uncertainty, and this can make model-based safety controllers lose their safety guarantee. We'll be mainly considering the control-affine dynamics, and the model uncertainty we will deal with is time invariant and deterministic uncertainty that can be captured by the vector fields f and g. Therefore, our setting is that we have a nominal model f tilde and g tilde that might be different from the triplet f and g. In this project, we wish to use the power of data because from data we can learn just the right amount of uncertainties to compensate, and also the structural assumptions about the uncertainty can be minimized. I'll first explain how the model uncertainty affects constraints on the control input that encode our stability and safety objectives. The constraints that will be used to encode the control objectives are designed based on control Lyapunov functions and control Bayer functions. Just to give you a quick summary, when the control input U satisfies the CLF constraint along the trajectory, it can exponentially stabilize the system. In contrast, with the CBF constraint satisfied, we can guarantee set invariance and use this for safety control. And these constraints can be incorporated in a min-norm optimization controller, which is a quadratic program. Now we'll see how model uncertainty affects our CLF constraint. Note that we denote nominal model-based quantities with tilde. Our true Lie derivative of the CLF V dot is LFV plus LGVU. However, this is different from our model-based estimate V dot tilde, Therefore, there exists a mismatch term between v dot and v dot tilde. We'll call this mismatch term delta. Note that delta is affine in U due to the control affine dynamics. Now, we can formulate a learning problem for delta. This can be solved effectively by using either reinforcement learning or Gaussian process regression. And once we learn the uncertainty effects in our constraints, we can formulate a min-norm controller that addresses the effects of uncertainty on the constraints, and therefore that can recover the desired control objectives for the true plant. So first, in the reinforcement learning setup, we use the R policy as a proxy to the uncertainty terms in the constraint. Since we can get v dot from numerical differentiation, the loss of the policy can be determined by measuring how well the policy estimates the true uncertainty. With this loss signal, we can train an R policy through simulations. Then, based on the learned estimate of the true CLF and CBF constraints from the policy, we can design the RL-based safety controller, so-called RL-CBF-CLF-QP. We demonstrated this framework on a biped walking on stepping stones. After this work, we turned our attention to Gaussian process regression, because Gaussian process regression can provide probabilistic guarantees of its prediction error. The objective is very similar. We apply GP regression to the mismatch term in the CLF or CBF constraint delta. But in doing so, we propose a specific kernel function that can capture the control affine structure of the uncertainty term. Using this kernel can also lead to a specific structure in the mean and variance terms of the prediction, which makes us possible to formulate the chance stability constraint as a second-order cone constraint. As a result, when incorporating this constraint with the min-norm objective, the resulting controller becomes a convex program and has a probabilistic guarantee for satisfying this stability objective. We have demonstrated this SOCP controller on a few different types of numerical examples. We've also done some interesting theoretical analysis on how the feasibility of the SOCP can be guaranteed based on the condition of the data distribution. For the next steps, we are working on improving the scalability of our framework by taking the sparse GP-based approach, and are also working on high-dimensional examples. For more details, please refer to these papers, and thank you so much for listening to my talk.
Hello, my name is Kim, and in this talk I will give you a brief overview of our work regarding predictive safety filters for learning-based control. Our basic motivation is to leverage machine learning advances to automate large parts of control design. The problem, however, with many machine learning techniques is that it's difficult to provide safety guarantees during learning. In particular, certain learning algorithms can only ensure safety after a successful learning procedure, which means that during certain learning episodes, as depicted here in the quadro examples, we can encounter safety constraint violations, for example, crashes into the ground. To overcome this limitation, we propose to include a safety filter in the closed-loop system. The safety filter sits between the system and the learning-based control module, and the task of the safety filter is to decide if a learning-based controller can be applied to the system or if it has to be modified to ensure safety at each time step during training episodes. Therefore, the question in this talk is how to obtain such a safety filter. The essential mechanism of the safety filter module is based on a safe backup controller. So if we take, for example, a car where the safety constraints are to stay on the road, we perform the following steps in closed loop. Based on a requested learning-based controller input, we check with the backup controller if for all future time steps the system will stay safe. If this is the case, we can directly pass through the learning-based controller. If this is not the case, as for example depicted here, where the backup controller can't ensure safety constraint satisfaction for all future time steps, we can resort to our previously computed backup trajectory to ensure safety. We implement this predictive safety filter using more predictive control ideas. meaning that we try to match each requested learning-based control input with an online computed backup trajectory that results in a safe terminal set, thereby ensuring safety for all future times while implementing the desired safety filtering property. By borrowing ideas from MPC theory, we avoid explicit computations of safe sets and safety controllers, which means that the safe set and safety controller is implicitly given by the predictive safety filter problem. And it's important to note that efficient solvers from MPC literature are available to reliably solve those problems in real time at each control sampling time step. This allows also for an application to larger scale systems. It's important to note, however, that in case of learning-based control, we can't typically assume that our prediction model is known. So we'd like to automate the process of obtaining a prediction model using some available system data. To this end, we developed several methods for different model assumptions, including approximately linear systems with uncertain parameter distributions and unbounded additive process noise, but also methods tailored to nonlinear systems. In addition, we can also extend the predictive safety filter idea to distributed systems. Similar to distributed MPC theory, we can then also leverage only local information to ensure safety for the entire distributed system. In the following, I'll briefly introduce to you two concepts for approximately linear systems and nonlinear systems. So in case of linear systems, we can support also unbounded process noise by introducing a so-called indirect feedback mechanism, where we only incorporate the state measurements in the objective function to obtain rigorous closed-loop satisfaction guarantees. And in the nonlinear case, what we do is we plan only backup trajectories in so-called confident subsets of the state and input space, thereby reducing the level of conservativeness. A recent application of the predictive safety filter to a miniature race car platform, also presented here at IROS, demonstrates, for example, how a human driver can safely learn to drive with the proposed safety framework, but also demonstrates the combination with a learning-based control approach, where we use imitation learning to accurately model an expert policy using a deep neural network policy approximation. The whole procedure can then safely be executed on the physical system. With this, I would like to conclude this talk about predictive safety filters, which provide a separation of performance and safety in learning-based control, and which are based on extensions of robust MPC theory as well as stochastic MPC formulations. Thanks for watching.
Okay, this concludes our invited Spotlight Talk session. We would like to thank our speakers for contributing to our workshop, and also thank you for joining us. We would also like to remind you of our live session taking place on September 27th from 4:10 to 6:10 Central European Time. And also check out our webpage on Safe Robot Learning with additional resources on this topic.